Hi, and welcome back to our next section of Unit 0 for Software Development and Secure Software Practices. This is our section on malicious code and application attacks, which is referenced from the CISSP Chapter 21. So again, finishing up the back of the book before we really get started. In this section, we're going to discuss malware, prevention, application attacks, and then just touch on a lot of different attacks and different ways that you can protect yourself from those from a software point of view. Let's get started. Following our roadmap for the ITS 277 class, as you can see, we're finishing up the introduction with this chapter on attacks and malware before we start really getting into our software assurance. Our first section on malware is going to discuss different types of malware or bad software and how those are going to go into your programs. I'm assuming at this point in your journey, you probably have heard of all of these at one point or another. So I'm not going to get into huge descriptions of each of them, but I am going to give you a little bit of a kind of survey of the different types of attacks. Our first section is going to be on viruses. Viruses were the first type of malicious code that we were able to recognize and work through. The purpose of a virus is to both propagate and execute its payload. So you're going to be doing some sort of a download and it's going to install some sort of malicious code onto your computer, which is then going to find ways to replicate itself from that software and execute its payload, which may be the same thing and they may be two separate sections of the virus. There's a lot of different ways that you can get infected. The first that we talk about is the MBR or master boot record. We are going to go more into this when we get to the file internal section of this course. But a basic covering of the master boot record is that it's the software that is going to be run on load when the boot is loaded, when the computer is booted up. Usually, an MBR is only about 512 bytes, which means it's very small, and you can't usually have your payload in that. So the virus that it works on an MBR is going to actually reference an alternative location, either in memory or outside of the computer itself, to be able to pull in that payload. Another option is our file infector. So it's a slightly modified executable COM or MSC file that is designed to replicate itself. Along with file infectors are companion viruses. So these are self-contained executables, but they have a similar file name. So the way that Windows generally will run is that they will first look for a file named COM, and then they will look for an executable, exe, and then they will look for a bat file. So if you have a game that's named game.exe and I make a virus that's called game.com and you go to a command prompt and you type in game, it's going to look for a COM first and then it'll look for the exe, which means you will inadvertently run the wrong file. You will run the .com because that will be pulled up first. So this is called a companion virus. Essentially, it's a virus that has a companion to another type of name. Our macro viruses are the ones that are usually written in VBA and attached to a Word document or an Excel document or something that's going to run macros. Both the Melissa and the I Love You viruses were both macro viruses. And then our last type of virus in this section is the service injection. So a lot of things on your Windows device, like your SVC's host or your Win login or your Explorer, are all things that are running all the time. So all we need to do is name our virus service or explorer.exe, and all of a sudden you have a second service running in your processes that is also called Explorer. Now you know what Explorer is, but if you have 17 versions of Explorer, which ones of those are viruses and which ones are legitimate? So these are called service injections, taking advantage of the fact that you have the service running under the exact same name. When it comes to viruses, there are different styles of viruses. The multi-parent virus is just a different propagation technique. So it can do a file infector and an MBR, or a macro virus that then does a service injection. So it has more than one propagation technique. Your stealth viruses are designed to tamper with your OS so that the antivirus software can't find it. If this is something that is generally running from your OS, stealth viruses do this underneath. Your antivirus isn't going to notice it. Polymorphic, from multiple forms, polymorphic, modifies their code as they go along. Imagine every time they change or they propagate, they add a 1 to the end. Well, your entire signature is going to change when you change that. So polymorphic viruses modify their signature as they go along so that virus signature detectors can't find them. And then, of course, we have encrypted viruses. These use cryptography to avoid detection. We're going to take our entire virus and we're going to crypto or hash it or do something along those lines to make sure that the virus checkers aren't going to recognize their signature. Basic viruses. The next section is going to be on logic bombs and Trojan horses. So a logic bomb is the idea of a virus that is going to stay dormant until the triggering event. Logic being that there's a Boolean yes or no, did this event occur? That event can be a specific time or perhaps a keystroke or a specific program that gets launched, but essentially there's a triggering effect that when something occurs, that's when the bomb happens. This is similar to the idea that you have a bomb underneath a car, and when you turn on the engine, that's when the car explodes. It doesn't explode just randomly. It explodes when you turn on the engine or when it hits a certain timer, something along those lines. Those are logic bombs. Trojan horses, on the other hand, appear to be, and sometimes actually are, legitimate software. They sometimes include the malicious payload underneath. So examples of Trojan horses are like rats, remote access Trojans, which open back doors which grant access. So we're going to install this piece of software, which we downloaded from the internet, which we know never to do, but we're going to do it anyway. Downloaded the software from the internet, and included in the software when it got installed was a rat. So there's remote access. As soon as it has been installed, it sends a nice little ping over to whoever the host is and says, I'm now open. I am now able to open the back door and grant admin access to the hacker. Crypto malware is this kind of new concept that is designed to steal your computing power specifically for cryptocurrency mining. So for those that understand a little bit more about cryptocurrency, one of the ways to get more currency is to be able to mine it. Well, to mine it, you need to use computing power. What we can do is we can put this little extra Trojan horse on your computer, and you don't really notice a 10% decrease in your power, but that 10% decrease multiplied by 1,000,000 gives a huge amount of power for the purposes of mining cryptocurrency. We call this crypto malware. The concept of Trojan horses, logic bombs, and then, of course, rats come into the idea of botnets. So botnets is simply a collection of computers that have a single bot master. They can be hundreds, thousands, even millions of computers. And we use these, well, we don't, but hackers will use these for DOS attacks or DDoS attacks. So essentially, we could tell all 1,000 or million computers, hey, go attack this IP address all at the same time. You can do that by creating your Trojan horse that is going to have this little botnet hanging out in the background saying, I'm going to be dormant up until the point of, I want to run this attack. Or the bot master gave me instructions. I'm just going to hang out here, and as soon as the bot master sends me out the instruction ping, then I'm going to move forward. Worms are similar to viruses, except worms propagate themselves without having you do anything. So the worm gets onto your computer, and then it runs its own propagation to go get more and more attacking, more people it can look through and find ways to attack different computers in the network, so on and so forth. Some of the examples of worms that we have is the Code Red Worm from 2001. The idea of the Code Red Worm was to select hundreds of IP addresses at a time, check all 100 of those, and see who was running the unpatched version of Microsoft IIS, which was the web service run by Microsoft. If it did, it would deface the homepage. So you think that's the attack. No, that wasn't the attack. The attack was actually a logic bomb that was put underneath. So they were able to deface the web page. You'd notice your web page was defaced. You'd go in and you'd fix the web page and you'd move on with your life, not realizing that there was a logic bomb underneath. The logic bomb was actually intended to run a DDoS attack on the White House IP address, which they were able to find and resolve and change the IP address and make it all fine. The RTM, or the Robert Tappan Morris one, was a 1988 Unix attack. So 1988 was way before most of the internet existed as it is now, and it attacked Unix machines directly. There was a debug mode in the SendMail program that allowed the program to read the mail if it got infected. It would then use a password attack with a dictionary attack or some sort of brute force attack to break into the password. it would use the finger utility to be able to find out which users were logged in and then spread to any users using the trust relationships that occurred. So back in the 80s and the early 90s, we had a program called Finger, and that was the way that you could log into a specific computer and say, is John Doe available? Is he logged in? At the time, again, we weren't really overly concerned with security, so this was a pretty easy break. So this was especially attacked towards Unix machines at the time. And probably one of the most popular ones is the Stuxnet, which was the one that attacked the Iranian nuclear weapon program in 2010. It would search for unprotected admin shares. So on a local network, as you know, you can log in and you can say, I want to attach to this admin network or this network here. We're looking for admin shares there. And then we were able to take advantage of a zero-day attack on the Windows Server or the print spoolers to be able to connect to the system for people that had the default database password. The way this was spread was actually through sharing of USB drives. So the virus or the worm sat on the USB drive, and when you plugged it into the computer, it would attach itself. This one specifically, underlying all of this, was designed to look for the Siemens controller, which ran the Iranian nuclear program. There is some contention on whether this was created by a Western ally to specifically attack the Iranian nuclear weapon thing, or whether this was done by a hacker. There's more details on this, obviously, both on the internet and in your textbook. Other types of attacks include spyware and AdWare and ransomware. So spyware is designed to spy on your computer. It's designed to take your actions, your keystroke logs, so on and so forth, and transmit them to another location. Spyware is designed to figure out what is your login name and password and just send those back so that people can log into your account. AdWare is designed to do pop-ups or advertising on your computer. A lot of people get AdWare whether they intended to or not, and it'll be those little pop-ups in the corner that say, oh, by the way, you've been infected with 23 viruses. Click here and we'll make it all better. AdWare, or other types of advertising that come in as you go along. We sometimes call these potentially unwanted programs or PUPs. And they're any software that does an action that you really didn't want. Sometimes when you install third-party plugins, those can do that. So if you're installing a piece of software, the default action may be installing a PUP, and you want to avoid those. So you almost always are going to want to limit your installation. Never do the default installation. Always do a custom installation and be able to change removing any of those third-party plugins that you don't want. Sometimes companies get paid to add those in. They're not breaking any laws. You chose to do the install that was the default that included those. So you always want to be careful when installing software that you don't do the default admin, you do a custom or install, that you do a custom install and make sure that you remove any third-party plugins that you didn't want. Ransomware has become a huge problem recently in the last couple of years. It is essentially a weaponization of cryptography. Cryptography being able to take your contents and encrypt them, and you need to have the key to unencrypt them. What ransomware does is it will install itself on your computer, and then it will encrypt critical files on your hard drive or all of your hard drive. And then you usually get presented with some sort of a post that says, haha, you've been attacked. And if you pay me X amount of dollars or Bitcoin or whatever, I will give you the key to unencrypt your files. When the user gets that, they have the choice of how they want to do that. In 2020, the surveyed organizations that were asked about this, 56% said they were hit by ransomware. Ransomware happens all the time. If you imagine, out of all the thousands of people that were surveyed for this, half of them had been hit by some version of ransomware. One of the interesting things was after this came out in 2020, the U.S. Treasury Department of Foreign Asset Control actually said that payment of ransom to countries that are under sanctions is illegal, because when you're under sanctions, you're not allowed to do financial transactions with that company. So if we are attacked as a ransomware attack by a country that is under sanctions, which has become a conversation that has occurred recently, paying that ransom is technically illegal. You need to contact the Treasury Department to find out how you want to handle that if that becomes a problem. This may be an actual issue as time goes on, depending on how the world chooses to change. Our next is on malicious scripts and zero-day attacks. So malicious scripts are a script that is written. So when you have automation or scripting, like PowerShell or Bash or Python that allows scripting and automation to be efficient. It's also a very easy way to gain access without actually writing to disk. Most malware programs or anti-malware programs are designed to look at the files that are saved on your drive. But if you're able to write a script and the script is run entirely in memory, then you don't have to worry about the malware program or the antivirus recognizing it. You never saved it to memory. We call these fileless malwares because they're run entirely in the memory, and that way the antivirus programs aren't able to find them. And the last section on malware is zero-day attacks. So the concept of a zero-day attack is that a vulnerability is introduced at some point, but nobody knows about it yet. So there is a point at which the hackers are able to find that vulnerability before the developers are able to create a patch. Obviously, we can't protect against a virus that we don't know anything about. So it's a security flaw that occurs, and there's this window of vulnerability from the time that you install the software up until the time you install the patch. If you have a delay in patching your software, you run into your window of vulnerability. That is from the time the software is introduced until the patch has been released. You also have a delay in applying the updates, which is where most of these attacks are going to occur. Because sometimes the hackers don't even know until the patch is released, and then they're just waiting for the lazy administrators or the administrators that are waiting to do testing on that patch to be able to find out whether or not that patch is going to cause problems. Zero-day attacks occur in between the time that the exploit is released and the attack signatures are released so that the antivirus can be prepared for them. In this time, the vendor is trying to find a fix and to resolve it. Always being aware of the fact that zero-day attacks happen all the time. We want to make sure we focus on defense in depth as security administrators or as system analysts to be able to be aware of zero-day attacks, prepare that they occur, make sure that we always have a secondary and tertiary way of solving those attacks if there is a flaw that we don't know about yet. We're now going to discuss different ways that you can protect yourself from malware, including which platforms are the most vulnerable, some anti-malware software, integrity monitoring, and some advanced threat protection. So according to the AV Atlas portal, which there's a link on your slides, the most common operating system, obviously, is going to be the most attacked, which is Windows. So Microsoft Windows is generally somewhere between 80 to 90% of the attacks that are out there. Malware and potentially unwanted applications, PUAs, by operating system. That doesn't mean that there are no attacks against Linux or Android or Mac OS. It just means that they're not as common. There has been more attacks against Mac OS recently in the last 4 to 5 years than there ever was before. And that's because I believe more people are using Macs and therefore there's more benefit to hackers to attack those. But it's always a good thing to keep an eye on things like the portal and be able to recognize how often and which platforms are the most vulnerable to attack. Different types of anti-malware software exist in the world. So there's two main styles of anti-malware software. The first is what we call signature-based. Signature-based anti-malware software maintains a database of all of the virus signatures that it uses to describe all of the different viruses that it knows about. So according to VirusTotal or any of the other sources that are out there, there's a big list of this is the signature for this given malware. When you download a file, your file signature is compared to the signature of the database to find out if your software that you just downloaded, your file, is a form of known malware. We call this signature-based detection. Once it has been detected, the software, the anti-malware software, can do a couple of different things. If it has the ability to remove it, it can remove it, disinfects any infected files, and returns your entire system to a safe condition. Sometimes it's recognized but can't be removed for a couple of different reasons. Maybe it's in a section of the hard disk that can't be touched, or it's actively in use. For other different reasons, it can't remove it. So what it can try to do in that case is quarantine it. Take the file, put it into a safe location, and then warn the administrator of the computer that this file has been identified as malware and maybe it needs to be identified and examined further. Finally, if it cannot be quarantined, it may choose to just delete the file as it is. As opposed to trying to remove it and disaffected it, we can just remove it. Better safe than sorry, get it out of your computer. The problem is these types of anti-malware software protection is only as safe as the database of signatures that's kept updated. So if you don't update that signature list, you can't be getting any of the new attempts that are coming through. The second form of anti-malware software is what we call heuristic mechanisms. What this software does is it doesn't look at the database of software signatures, it watches the behavior of the file. Is the file saving itself, maybe copying a lot, maybe is it doing a lot of disk lookups, is it doing some connections to the outside world? What is the behavior of the file, and is it a behavior that might be something malware? So if you download a piece of software that is constantly going out to the internet, pulling in files and downloading them onto your computer, that might be a form of malicious software and therefore needs to be quarantined until you can verify, no, that's what I intended it to do. So heuristic mechanisms are a way of anti-malware software to be able to identify viruses without having that signature. This is a great way of looking for zero-day attacks. Another way of preventing is using integrity monitoring. What you can do with integrity monitoring is look at the actual signatures of the files that are on your computer at this moment. Are those the same that they are in the next moment? So essentially, if I have this file, say my Microsoft Word file or my systems file or something in there, and I know what the signature is of that file, I can check that file daily, weekly, monthly, whatever, to find out if that signature has changed. Now, some things change often, and some things shouldn't change at all. If it is something that shouldn't change at all, integrity monitoring can tell you, hey, someone tried to change your systems file. That shouldn't be happening. So integrity monitoring will allow you to detect things like files have been changed. We use them for website defacement. Someone's going to go into your web server and change your page. That page has now been changed. We can check that. We can also check and see if programs have been modified because obviously by modification, those signatures will have changed as well. What can happen is the integrity monitoring will create a hash table of all of the file signatures, and then it compares those to the existing files every X amount of time. We can also use user and entity behavior analytics to build a profile of what the user tends to do to make sure that you're prepared if somehow that behavior alters or changes. Another way that we can protect is using advanced threat protection, or ATP. Endpoint detection and response, or EDR, is a way to analyze your endpoint memory and activity, automatically isolate your activity, anything that looks like it's doing something weird. It can give you real-time dashboard insights, and then make sure that your response is appropriate. Our next section is going to cover application attacks, as opposed to web applications, which is in the next section. Application attacks cover buffer overflows, time of check to time of use, backdoors, and escalation privileges, and rootkits. So our first examples are buffer overflows. A buffer overflow occurs if the software isn't checking the size of the item that is stored. So if I'm expecting to store a single byte or 8 bits, or a buffer of 8 bytes in the example given here, to store 8 characters. Each character fills in a byte. We have 8 bytes. We're expecting to be storing 8 characters. And my user puts in 10. It can store the original 8, and then the remaining 2 bytes are going to overflow into the next variable space. If that next variable space is something important, you can use buffer overflow attacks to fill in the buffer for a given space, and then have that overflow change the value of variable that exists in the adjacent memory location. So that's how hackers can use buffer overflows to change memory that is not actually available for them to change. The time of check time of use, or time of check to time of use, depending on how it's acronymed out, is what we call a race condition or a state attack. What happens is you're going to go through and you're going to check the status of something. If that status changes prior to the use, it can then be used even though it shouldn't be. We're not checking the status before it gets used. So how long is it between the time that you checked and the time you actually used it? In some cases, these can be seconds, minutes, sometimes they can be hours. If I'm going to log into a system, I've only checked my login once every hour. And then over that hour, somebody has gone through, found out that it was hacked, found out that it was hijacked, some other version, changed the password, but I haven't changed my time of check a second time, which means that the people who have hijacked in can still use it. Time of use needed to do another time of check. You're racing against that time to figure out what is the state of the object. If you want to replace the data file after the identity has been verified, but before it's actually been read, is another option of a race condition. Race conditions, or time of check to time of use, is a way of making sure that you check it often enough, but not so often that it becomes detrimental to your user use. Another version of application attacks are backdoors. A backdoor, by definition, is an undocumented command sequence designed to bypass authorization. Okay, so programmers tend to put in these type of backdoors to bypass authorization because they're trying to run through the workflow often. They want to run it multiple times, and they don't want to have to authorize every single time. It's exhausting, and it's kind of annoying, and so they throw in this backdoor really quick just to test something. Sometimes they forget to remove it. So sometimes a coder leaves a backdoor in purpose because that says I can go back in and check something often, or it's left in on accident. Either way, it is an undocumented way of bypassing your authorization. Once it becomes known, other people can use it as well. The other version of this would be a rootkit or privilege escalation, and this is where the software or the malware is designed to get in as a normal user or a guest user and then upgrade to an admin as time goes on, so that we now have admin or super admin permissions from just a regular guest user. So rootkits are designed to increase your privileges, assuming the super admin can do anything he wants, whereas a user is not able to see a lot of things or do a lot of things. Increasing this privilege is a way that people attack applications. Our next type of vulnerability is our injections. Now, injection vulnerabilities used to be the most common web application attack in 2020, or actually for the last couple of years. It's been replaced with a couple of other things now, but it's still definitely in the top 5. Injection attacks can include SQL injections, code injections, and then command line injections, and we'll go through each one to describe what they are. So our first one is our SQL injections, and you need to have a basic understanding of what databases do to be able to understand how a SQL injection attack occurs. When you use databases, you use SQL or structured querying language to be able to attach to the database, which we've covered. Those queries that you ask usually will take some sort of input from the user to be able to ask for certain things. In the example below, I want to get all of the items, descriptions and prices, where the item is either an orange or a tiger or a pillow, because I'm looking for an orange tiger pillow. If the user or the hacker in this example, instead of writing orange tiger pillow, writes orange tiger pillow, single quote, semicolon, select customer name, customer credit card number from orders, and then adds in some comment code to make the extra space and colon or quotes be not used, we can now run the query that says, select the item description, so on and so forth, that's tiger and orange and pillow, and then get me the customer names and credit card numbers and return those as well. If this works, then the hacker is now able to view all of the customer names and credit card numbers by changing the query that was actually run. A similar example is the second one down here, where we're selecting first last names where the account number is 52019, because that's the account number we want. And what the hacker does is say 52019, or where 1 is equal to 1. Since Boolean expressions are used in this example, we're going to get the first last name and balance from the accounts where either the account number equals this one or 1 equals 1. Well, 1 always equals 1, so that part of the Boolean check is always going to come back true, which means we're going to get all of the records, every customer last name and balance from the accounts table. This is a way of being able to recognize information from your SQL database that was not intended. To check for this, you can run some blind content to test to see whether or not there's any validation code run on your SQL statements. We can also do some timing checks where we can check against a delay. There's a SQL command that says delay for 15 seconds or something like that. If I'm going to run the delay for 15 seconds and my result comes back instantly, I know that that command isn't being run through a stored procedure. If it is waiting 15 seconds, then I know that that test was able to run, which means I can run any SQL code I want by just writing that into my input. The way we solve these is through input validation, making sure that the user does not have the ability to enter in single quotes or statements or anything along the lines that would allow them to run SQL injection attacks. Our code injections are where we insert malicious code into a legitimate web code. We can use LDAP injection or XML or DLL to actually load dynamically linked libraries or target XML applications. We are actually inserting code into a legitimate website. We can use input escaping and validation, again, to always make sure that we prevent these injection attacks. And the last example here in injection attacks is command injections. Imagine that you have some sort of a procedure that asks the user to enter in their username. In this case, we used M. Chappell. That was the name of the author of the book. And the code that is going to run when we do that is it's going to create a directory for that person under Home Students M. Chappell. And it's going to run the make directory system command. Well, if I know that it's going to do that and I change M. Chappell to be M. Chappell and remove directory home or something along those lines, or reformat or change user access, so on and so forth, suddenly both of those system commands are run. So being able to do a command injection takes advantage of the fact that you're taking user input and running a system command based directly on that to chain your commands together to run multiple commands. Again, input validation is going to help to prevent this. Make sure that you never submit anything or allow the user to submit something that could possibly be used in this way. Our next example is how hackers are able to exploit authorizations. So we've talked about multi-factor authentication and authorizations that we do. In this case, OWASP, the Open Web Application Security Project, has their list of web application security risks. Those include now authorization vulnerabilities. So insecure direct objects, directory transversals, and file inclusions. So again, we're going to go through each of those specifically and describe how those are used. You may have noticed at some point that you go to a website and you want to reference a single file or a form, and you use some sort of PHP to say, get the document, and then we give you an ID number for the document. In the example here, we have the company, and then we're going to get document 1842. Well, if there's a document 1842, what are the chances that there's document 1841, or an 1843, or an 1844? By using this type of insecure direct object reference when you use a query string, hackers can intuitively figure out additional documents as they go along. By using the PHP option of get document, that doesn't do any extra validation to make sure that that's a problem, goes ahead and gets that actual value. So we call this accessing objects insecurely without going through some sort of validation. Another problem that's occurred is what we call directory transversal. And this has become a problem not only for most web servers that are on a network, but can also be a problem in cloud environments. Directory transversal allows you to navigate to unauthorized areas by just using directory transversal, being able to do the ... to go up a directory. So in most Apache websites, you usually go down the var directory and then into the www directory and then into the HTML directory, and you go find your index.html. That's where your normal pages go in Apache websites. Well, if all I have to do is do ... I can go up directories and I can transverse through up the directory and then back down another way to find the etc directory, maybe the shadow directory, anything that I want inside of there. Making sure that there is no direct directory transversal available on your server is a really important way to protect yourself from authorization vulnerabilities. And our last one for this is file inclusion, allowing the attacker to fool the web server into actually executing code by using an uploads directory or by using an include statement in a PHP command. Again, a lot of these are PHP-specific attacks, which is why some people are leaning away from PHP because there are such risks in using it. Local file inclusions allow the hacker to upload something to an uploads directory. Assume that you have a www.uploads, and we're going to attach this file. When the hacker uploads the attack.exe file into the uploads directory and then includes the include query parameter in his file parameter, it will automatically attach that file. If that exe file does something to the server, that is a really easy way to do a local file inclusion attack. You can also use the exact same notation to go find a file from a remote location. This is so much easier because the attacker doesn't have to know where the location of that uploads file is or even include that file on the server. The server will run the file and nobody will even know where it came from. Sometimes these attacks create a web shell that give access to the server over HTTP or HTTPS, which makes it less detectable by your anti-malware projects. Specifically exploiting web applications include cross-site scripting, request forgeries, and session hijacking. So cross-site scripting allows the attacker to add HTML code in the form of JavaScript into an existing web page. Two different ways to do XSS, or cross-site scripting, X being cross. Reflected XSS is where the website is going to show the input reflected into the next page. So imagine that the page asks you to enter your name, and you say, my name is Cheryl, and the next page says, hello, Cheryl. So it has taken the script that you have run, put that into the text of the next page, and it should now say hello and put in that value. If you enter your name as Mike with a script tag and then run some JavaScript, the page will pop up now with an alert when it runs that page. You can imagine the script being much more nefarious than an alert pop-up. Again, input validation is going to help you with this. Stored or persistent XSS is going to allow you to store that script on the web server, so it'll remain after the attack occurred. You can imagine this in a message board or a comments list. Every person who runs the page now has the script run to view those comments. Instead of seeing the comments, the script will run on the user's computer. Redirection, request information, performing another attack are all different things that you can do with these persistent XSS attacks. The cheat sheet from OWASP that I've included at the bottom here gives you a way of finding out how the script is used and making sure that you do your input validation to make sure that you prevent them every time a user enters input. Our next web application vulnerability is request forgery, or cross-site request forgery, which is sometimes with an X or a C SRF. In this case, we attack the trust that remote sites have in the user system. So imagine, as most people do, you open 3 tabs up on your computer. One of them is going to Amazon, one is going to your bank, and one is going to Outlook. And then you go to another site on the same tab, and you say, go look at the comments for some news article. Included in those comments is an attack saying, hey, what are the chances that this person on this set of websites is logged into Amazon? Can we take advantage of the token there? Can we log into Outlook from that and being able to take the login that you've already done on a secondary tab and use that session to have the hacker do what they want? Open it up, go in and make changes, maybe transfer money from your bank account to another bank account. The protection for this is making sure that you secure tokens, you don't include the links, and try not to open up multiple tabs when you're doing things like this. If you're going to be opening up your bank account, open it on a single tab, close it out when you're done, try to make sure you close that session. The server-side request forgery tricks the server into visiting a URL via user input. So when you tell the server, this is a piece of information and this is where I want you to go get it, make sure that the server is going to validate that site as well and make sure it's not a nefarious site. Session hijacking, similar to the cross-site, intercepts the connection between the user and the server and then takes over the session. Different ways you can capture detail of your authentication sometimes tricks the client into thinking that the attacker is the server, so they enter in their password information or things like that. or accessing the web application using the cookies and the information there so that they can make changes that the user would be able to do if their session was not hijacked. Again, application controls, cookie management, administrative controls can all be used to prevent session hijacking. We're now going to spend a little bit of time going over those application security controls that we're going to be able to use to try to prevent these attacks that we've just discussed. We're going to cover input validation, web application firewalls, database security, and code security. So probably the most important protection you have against attacks is called input validation. We've talked about it before. The user is going to enter stuff into the computer, and if he is entering stuff into the computer, that could be some sort of an attack. We need to validate that input and make sure that we protect the information coming in. So every time a user inputs something, that could be an attack. Be aware of that. Two different ways that we like to handle this is either input whitelisting or blacklisting. Whitelisting allows us to say these are the only values that are allowed. For example, a date. It should be a date that's actually appropriate. If it's a date that should be from now until the future, definitely shouldn't be a past date. We should validate against that. Make sure that we didn't put in 13th month or something like that. If it was an age, 0 to 120, negative ages shouldn't be appropriate, and an age of 467 probably doesn't make sense either. It has really limited use in some cases where it's like a name or an address or something that you really don't want to have every single name or address listed in some sort of a whitelist. But if you can limit your exact values by using a drop-down or something like that, you limit a whole lot of options for people to hack into your system. The other side of this is what we call input blacklisting or block listing. It ensures that certain input is not allowed, such as script tags or comments in SQL, things like that. You describe what is not allowed or blocked, and that's called input blacklisting. So whitelisting and blacklisting describes either what is allowed or what is not allowed. Input validation should always be done on the server side to prevent the hackers from overriding the validation. If you put this input validation on the client side, the hacker can go into the code on the client side and change it there. That doesn't mean the client-side validation isn't useful. It is, but it also can be hacked. So you always want to make sure that you always have server-side validation and adding client-side validation as well. Some of the things to be aware of are what we call meta characters. They are characters that have a special programmatic meaning. So quotes, single quotes, double quotes, brackets, braces, backslashes for an escape character, semicolons, things like this. Anything that could be used in a programming language probably should be removed as much as possible. Now, if you're going to have to allow a single quote because we're going to allow contractions in the text that you're about to enter, that's one thing, but you want to make sure that you're very careful about allowing those things and that you run input validation as much as possible. A web application firewall is designed to protect your web server and protect your internal network because programming can only protect it so much. You have to have some sort of hardware or networking options in there to protect your network. First, from the outside internet into your internal network, you should always have a network firewall. Prevents only certain protocols from coming through. Once you get into the network, you should have a specific dedicated DMZ or demilitarized zone where all of your web traffic is going to be sent through. That is not the same direction as your internal network traffic. All web traffic on port 80 or 443 for HTTPS should always be going through your DMZ and then passing through a web application firewall. That web application firewall can protect your web server as well, knowing that everything coming through there should be coming from the DMZ and it should be protected as much as possible to make sure that changes don't get made to your web server inadvertently. When it comes to your database, we can run parameterized queries, which are queries that are created in advance and validated input is used as a parameter. We can also use stored procedures, which are similar to a function where we can have validation inside of that code. Make sure that only things that should be acceptable to the database are run inside of those stored procedures. Running parameterized queries or stored procedures limits the options for your hacker to run SQL injection attacks. The other way that we can handle database security is using the concept of obfuscation and camouflage. Obfuscation is just the idea of trying to make things more confusing or more unclear. We're going to try to muddy the water a little bit. First, always limit the data that you are collecting. Don't collect sensitive data if you don't need it. Don't ask a random user for their birth date. That's private information unless there's a reason you need to know their birth date. As soon as you get rid or finish using your sensitive data, try to dispose of it as soon as possible. The less data you have stored on your database, the less chance you have of a hacker getting hold of that. We can use tokenization to replace personal information like a social security number or a date of birth with some sort of a unique identifier, a GUID, or a globally unique identifier that can be created randomly rather than putting in personally identifiable information. Use a token. Use something that is not able to be used by a hacker. We can also use hashing, which is a cryptographic algorithm of sensitive info. If I need to be able to compare a password, rather than storing the password as clear text in my database, I can take the password, hash it with some sort of a salt, which is a random number, or even the username, run it through a hashing algorithm, and store that value. Then every time the user enters their password, run it through the algorithm, and if it matches the hashed value, I didn't have to store that password. Using hashing is a great way of protecting sensitive information in your database. Different ways that we can use code to give us some security. First off, you can sign your code. Confirm the authenticity of your code by digitally signing it with a private key. Make your public key available, and the public key can be used to decode the signature to make sure that it really came from you, verifying that signature. This is used a lot when code is being reused. So code reuse refers to the aspect of using libraries or SDKs that have already been verified by another user, by another company. When you buy things or use code that has already been verified and determined to be secure, you are protecting yourself. You don't have to run through the additional tests, although you always want to check to make sure that those libraries and SDKs have gone through the same testing and security functionality that you would do at your company. Software security or diversity is a way of avoiding a single point of failure. If all of your software is from the same vendor, you have a single point of failure. If that vendor is attacked, all of your software is at risk. If you're using a single library for all of your software, that's a single point of failure. If someone can break into the library, they can see all of your software. Try to diversify your software as much as possible. We've talked about code repositories, or essentially having a central location for all of your source code. This is useful both for source control and for version control to ensure that the code that you are being used is the correct version. Using hashing to make a code signature or some sort of a file signature to ensure that the integrity of that code has not been changed since it was verified. It's a great way of getting an MD5 hash or something of a specific file and ensuring that file is exactly what the vendor intended to hand you. When you make an application, you want to make it as resilient as possible. Resilience, when it comes to an application, refers to the ability for it to scale as necessary. If you make an application and you only test it with 3 users, and then you put it out there for the internet to use and 100,000 people attack it the one day, your computing power or resources may not be strong enough to handle the increased demand. Make sure that your application is able to be scaled. Along with scalability goes along with elasticity. The application should automatically scale up and down as necessary to meet demand. If you have 100,000 people on day 1 and 10 people on day 2, it should scale back down to not use as many code resources as it needs. If it doesn't need as many, there's no point in scaling up and keeping it up there. So your resilience of your application should include both its scalability and its elasticity. And our last section is on secure coding practice. How do you code well to make sure that your code is secure? We're going to cover comments, error handling, hard coding of credentials, and your memory management. Comments. Comments are exceedingly useful for programmers, and often they'll be required by your development team. Comments will allow you to tell other developers what you're doing in certain parts of your code, to explain your algorithm, and to explain what it was you were doing at this specific point in time. However, If your code is being interpreted as opposed to compiled, that source code comments are available to the hackers. Do you really want to give that kind of information to your hackers? So some of the things that people do with their source code is they decomment interpreted languages to make sure all of the comments are removed prior to deployment. You don't want to give the hackers any more information than you have to. If your code is compiled, the comments are automatically hidden because all that is compiled is the actual binary necessary to run the code. So in this case, compiled code is much more secure than interpreted code. Another way that programmers can ensure that their code is safe is through error handling. Your code should never crash. It should never break the application. And to do that, programmers use what we call a try-catch block or try-except block, depending on which language you're using. A try-catch block will allow the code to try to do something. Sometimes when it does that thing, an exception or an error will happen inside of that code. What happens is we decide to catch that error or that exception and handle it gracefully. Sometimes you print an error, sometimes you simply apply a separate value to it, different error messages for different reasons. The try-catch block will allow the exception or the error to be handled nicely without crashing all of your code. The thing about error messaging is that from a programmer's point of view, you want to tell people exactly what went wrong so that you can make it very clear that what they shouldn't do again. However, from a secure point of view, you want to limit those error messages as much as possible to try to avoid giving too much information to the hacker. For example, when you log into a system, it generally will not tell you your username is not in the system or your password is not in the system. It'll simply say login failed, which means it could have failed for 12 different reasons. It might say login failed error 2, error 6, error 15, and that may mean something to the programmer, but it wouldn't mean anything to the hacker. So you don't want to give any more information than is necessary when you handle your error exception handling. Occasionally, when programmers are starting out programming, they hard code some information. It speeds up development. We're always going to attach to this database, so let's hard code in the password and the login information to the database. As the code is being built, we generally add authentication or authorization as it's going on. And we should remove any of those hard-coded pieces of information that we added during development. However, occasionally programmers will leave in some hard-coded credentials, maintenance accounts, some attachments to databases or other resources, maybe a key, certificate key of some type. Technically, hard-coded credentials are a backdoor. They allow access without using the proper channels. So what you always want to make sure you do is that you create your authorization and your accounts first and never hard code in that information. If it's hard coded, it's very easy to forget to remove it. What you'll find going into GitHub or other open repositories is that some people have left their hard coded credentials in the code. If you happen to use the same name and password for your hard coded credentials in your code in GitHub as you do for your bank, you just released your name and password to anybody who wanted to find it. Always remember to remove any hard-coded credentials prior to deployment of any software. As far as memory management, different languages handle memory management differently, but all of them are susceptible to resource exhaustion. Essentially, an application is given X amount of resources, memory that it's allowed to use, and sometimes it can use it all up. Different reasons for that can include memory leaks, where we stored a variable and then we forgot that we stored it there, but it's still stored. We just don't have a reference to it anymore. If you ever need to do that, we need to clean up that reference, return it back to the system so that we aren't using up that memory. We also have the problem of pointer dereferencing, where we have a pointer or an address in memory that we are referencing. This is, the value X is in this location, and we give it to a variable. Sometimes that address is actually null, which causes the system to crash. We want to always be careful about pointer dereferencing and memory leaks, depending, again, on the language that we're using. Some languages handle the garbage collection of cleaning up their memory better than others do. But it's always something you want to keep an eye on because memory management can be something that can be exploited with buffer overflows and other types of entries from users and attacks. So this chapter has covered a lot of different malicious code and attacks. Hopefully many of these you've heard of before, and this is just a review. Always remember, viruses, worms, Trojans, and logic bombs as different types of malware, ransomware, spyware, AdWare, how we do different attacks with buffer overflows, injections, backdoors, and rootkits, and web attacks with cross-site scripting, hijacking, and SQL injections. Remember, always focus on defense in depth. You always want to have multiple ways of protecting your data and your software, your hardware, and your entire environment from attacks. Always check your input validation. Make sure that you check anything that a user is ever typing in. And always have some sort of authentication to protect your network from outside attacks, using firewalls to make sure nobody can get in and access areas that they shouldn't be. Thank you for watching this video. If you have any questions, please leave them either in the chat or send them to me directly. Have a great day, and I'll see you for the next chapter.